Today's lecture is going to be a little bit different because we meet online. If this works out for both of us, we can use this method to teach from time to time when it's not convenient for either you or me to travel to campus. Alright, so let's get started now. Today it's going to be sort of like a continue from last Wednesday. It's going to be about the integration and the basic applications of that. So let's talk about what we did last Wednesday. So last Wednesday we did a couple of things. So let me take a note here. Last week. The first thing we did last week is about the basic rules of integration. All right, basic rules of integration. So it's about finding the antiderivative of a function. All right, so it's about the table of the formulas that I told you that you don't need to memorize as long as you know how to differentiate. All right. Okay, so after that we talk about the fundamental theorem of calculus number 1 and number 2. Fundamental. I'm gonna try to keep my handwriting legible to you because it's so hard to write on this screen. Fundamental theorem of calculus 1 and 2. We proved this in class, which some of you might not like because it requires a lot of steps and some math concepts that you might not be used to. But it's important that you know about this so that you know where your formulas came from. Alright, so we talked about this on last Wednesday, and we also talk about the substitution technique when it comes to finding integration, performing integration, substitution technique. Alright, so today we are going to continue on this and expand it a little bit more. Okay, let's by the way, you can download this slide from Canvas, so it's going to be a new slide for today's lecture. So let's move to the second slide here. Here, this is the formulas for the antiderivatives. That is basically the basic rules of the integration I talked about last time. I didn't go into the detail when I talk about this in class, so some of you might already find this easy to understand, but some of you might not, judging from the practice we did last Wednesday. So let me spend some time here explaining about these formulas. If you find this easy, you can skip to the next part. Alright, so this is about finding antiderivative of a certain function. But to me, I don't think you need to memorize much of this because it's the same as differentiating. For example, here we have this function x to the power of n, x to the power of something. We want to find the antiderivative of this, or basically we want to know what happens if we integrate this. So in this formula it says that if you integrate this, the power of this x is going to increase by 1, n plus 1. Alright, and then you have to divide this whole term by n plus 1. That is what the formula says. But I don't like to memorize this. In my head, I just think that if I want this, if I want x to the power of n, what do I need to differentiate? In my head, I know right away. I need to differentiate something with power higher by 1. So it's going to be this that I need to differentiate. Looking at this x to the power of n plus 1, if I differentiate this, I'm going to get x to the power of n, right? Exactly what I want right here. But then I know that if I just use x to the power of n plus 1 alone, if I diff that, n plus 1 is going to come down and appear in the expression. So in order to get rid of that n plus 1, I need to divide this by n plus 1 down here. So n plus 1 down here is here to cancel the extra term so that in the end there is nothing in front of x to the power of n. So try to do this. But if you don't like this, you can just use these formulas directly. So here, next one, sine of kx. So here we have this coefficient k in front of x. So let's see what happens here. We want to find out what happens if we integrate sine of kx. So you can take a look at these formulas and you can see some terms right here. But in my mind, I would think that what do I need to diff in order to get sine of kx? One thing I know for sure, if I want to get sine of something, I need to differentiate minus cosine of that. Exactly. So with this in my mind, and I think forward, if I diff cosine of kx, k is going to come out due to the chain rule. And in the end, there is no k in front of this sine of kx. So I have to get rid of that extra k in the end by divide that with k, just the same as what we did in number 1. Right? This k down here is for canceling with the k that is going to come out from the chain rule. Alright, next, integrate cosine of kx. I ask myself, what do I need to differentiate in order to get cosine? Oh, I know right away. I need to diff sine in order to get cosine. So I need to diff sine of that in order to get cosine. Alright, so with this k, it's there to cancel with the k from the inside, which is going to come out due to the chain rule. Same thing as number 2. Alright, so next, secant square kx. What do I need to diff in order to get secant square? And I think back about the differentiation formulas. I know that I have to diff tan. I diff tan, I get secant square. So tan is going to be right here. I need to diff tan in order to get secant square. And k also there to cancel this extra k that is going to come out. Same with cosecant square. I need to diff minus cotan. Same thing again. And with this k again. Right? And this keeps going. What do I need to diff in order to get secant tan? I need to diff secant. What do I need to diff in order to get cosecant cotan? I need to diff minus cosecant. So this is like differentiating backward. Right? Same with this exponential. Right? If you diff this, k is going to come down. Right? Exponential is going to be the same, but this time you integrate. You don't want that k, so cancel with that. You can see the pattern. We cancel these extra terms just the same for every formula. Also here. Now next one, we want to integrate 1 over x. Right? Many of you got this wrong because you confuse this with differentiating 1 over x. Differentiating 1 over x, you get x to the power minus x to the power of minus 2. But here you have to go backward, not forward. So go backward. You ask yourself, what do I have to diff in order to get 1 over x? And you can see that you have to diff ln of x or ln of absolute x in order to get 1 over x. Alright, now 1, 2, 3, 4, 5 until 9, this is something you have seen. But then we have this 10, 11, and 12. This involves the arcsin, the inverse trigonometry function, arcsin, arcsecant, and arctan. So let me expand this a little bit because we didn't talk about this much when we learned about differentiating. So this is the same as differentiating arcsin. So let's add this right here. We have this arcsin. of x, and then we try to differentiate that d of this with respect to x from the formula, differentiation formula. We get 1 over square root of 1 minus x squared. Alright, so this is differentiating, but what we see in this number 10, it's going to go backward. But then you see this coefficient k over here and over there, and some of you might find this confusing. So let's try to work on this arcsin down here to make it equal to what we see in the formula up there. So instead of this arcsin alone, we are going to add this coefficient k in front of x, arcsin of kx. Now with this, just perform differentiation normally. It's going to be the same pattern, except that the result here is going to be kx instead of x squared. So this whole term is going to get squared. You can think of this as u, sort of like substitution into that. So you diff that u is going to appear down here, u squared, just like x squared up there. But then with this, you have to perform the chain rule to diff u again, and diff u with respect to x, you are going to get k out of that. So diff that again, you get k from the chain rule. Now let's arrange these terms a little bit more. So I'm going to move this k to the other side, this k from the right hand side to the left hand side. So it's going to be 1 over k differentiation of arcsin, or I should say that derivative of arcsin kx. It's going to be equal to 1 over square root of 1 minus k squared x squared. Alright, and then what I'm going to do here, I'm going to move this dx. What about I do it right here? This dx is going to get moved to the other side of this equation. So this is going to get eliminated. Alright, and after that, I'm going to perform integration both sides. Alright, so after integration, I'm going to get this 1 over k arcsin k of x. It's going to be equal to the integration of 1 of over 1 minus k squared x squared, which means that this term inside, let me change that, I'm sorry, it's supposed to be red. This term inside is the antiderivative of this 1 over k arcsin kx. Right, this antiderivative, right, just the same as what we see in number 10, right? Antiderivative of 1 over k arcsin kx. Well, here you can put plus c here because you perform the indefinite integration. You are supposed to get the constant out of that, and antiderivative of that is the term inside this integration, right? Same as what we see in the table. All right. Now, here we have this two more formulas, which is the arctan and arcsecant. So let me add it down here alongside with the arcsin. So at this point, I'm going to erase the work that I did on the integration here. So this is going to be gone. All right, give me some time. Okay, I'm going to just keep the derivative of arcsin. All right. Now that is derivative of arcsin. We have two more. Derivative of arctan x with respect to x is going to be equal to 1 over 1 plus x squared. And if you do the same thing that we did that I did with the arcsin, you are going to get the formula in the table. Now another formula for the differentiation of inverse trigonometry is the derivative of arcsecant x with respect to x. You should get 1 over x square root of x squared minus 1. Alright, I want you to, well, memorize these three because we are going to use them later. Right? Diff arcsine, you get this. Diff arctan, you get that. And then arcsecant, something else. Okay? Now, you might ask, what about cosine, cotan, and cosecant? The thing is, if you know these three, the rest three is not hard to memorize. So the rest, d by dx of arc cosine x is going to be just very similar to arcsine, except that we have this minus sign in front. That's all. And for the derivative of arc cotan with respect to x, it's going to be almost exactly like the result from the arctan, 1 plus x squared, except we have this minus sign again. And same for the arc cosecant. X with respect to x, same as above, x square root of x squared minus 1, but with the minus sign in front. So please try to remember these because it's going to you are going to need them again. Okay, so so this is the formulas that you should get used to, and if possible, I don't want you to look this up. It should come out to you naturally, and of course that's going to come with experience from the doing practice problems and homework. Alright, so let's move to the next slide. Now this is about some properties regarding the definite integration. So definite integrations is the integration with starting point and the end point. Definite, right? You know where it starts, you know where it ends, and this corresponds with the fundamental theorem of calculus number 2. What it says is that if you integrate a certain function, fx, of course this has to be with respect to that variable x, and you know where it starts, x equal to a and ends equal to b. This is going to be equal to the antiderivative evaluated at the endpoints b minus the antiderivative evaluated at the starting point fa. So this is definite integral, and so and this related to the theorem number 2. So once again, this is definite integral. Well, I should say definite integration. So you can use this formula to find the value of your integration here. Now, I bring this up because when it comes to this definite integral, you have starting point, you have end point, you can play with it. Now let's take a look at these properties 1 through 5. What can we play around with this integration, right, with this form? Now let's take a look at the first one, the order of integration. This is about the order of the starting point and the end point. Here you can see that the starting point is b. Well, it's different from what I wrote up there, but you have to understand that down of the integration sign, that is the starting point. Right, this is start and this is end. if you somehow switch these two values, like if you have -2 for B and 2 for A, and then all of a sudden you switch A down here and B up here, what's going to happen is that the original value is going to become the result of this switching is going to cause the value to be negative of the original value. This is going to happen. Let me be clear to you. This doesn't mean that the result is going to be negative. Very important. Does not mean that result is negative. No, that's not right. What this means is that whatever you have from the beginning, from this, if it's positive and if you switch that order, it's going to become negative. But if the original is negative, the result of switching would be negative of negative. That should be positive. So the switching is going to cause the result to be negative of the original value. All right? Different from the result is being negative. Different thing. All right? So just change the sign, basically. I don't know if I made you more confused with this, but let's just say that switch sign. All right? Positive to negative, and negative becomes positive. All right, next one is the zero width. What does that mean? So let's take a look here. What we have right here is that starting point is A and end point at A. Imagine this function in the space, and then you try to find the area starting at A. Try to find the area under the graph starting at A and ends at A. So this is no area at all, right? So the area would come out to be 0. Because there is no area under the graph. No area under graph fx. I wrote this too fast. I don't like it, so let me fix that. Give me some time. So this doesn't mean it is negative. All right. It's just the opposite sign. Okay. Now, next properties with the definite integral. It's about the integration of some certain function multiplied by a constant. So you want to integrate fx, but then you have this constant coefficient k in front. This is just like in differentiation. You want to diff a certain function with constant in front of that. You can just take that constant out of the operation. Not out of the operation. I mean, you just perform operation on the function directly, and then in the end, that constant is still there. So you can just take this constant outside and then perform the integration directly to the function itself. All right. Now, what about minus sign? Minus sign is the same as constant k equal to -1. You see this? You don't need to get confused. Just take it outside and perform the integration directly to f. All right. Once again, I saw some of you got confused about constant. Constant, if it's multiplied to a certain function, you don't need to worry about it too much. Just take it outside of the operation. But if constant is alone, then that is different. Okay, so keep this in mind. It's different things. Constant alone and constant multiplied to a certain function. Now, next one. This property, sum and difference. So in this case, you want to perform the definite integration of two functions. So we have this fx and gx, and they are summed together or subtracted from each other. So in this case, you can just distribute the definite integral into each one of them. And then the sign of this operation, link between them, still the same. All right. So just distribute the integration to each function. Now, last one, I find this interesting. Additivity. So what's gonna happen here is that, what about we take a look at the meaning of this integration? First one, we perform integration of this function fx starting from a to b. So you can think of this as the area of fx starting from a to b, right? Then plus another term. This is the integration of fx starting from b to c. So this is the first one is the area from a to b. And the second one is the area from b to c. So you can see that they have common junction point. It connects to each other, which means that the whole thing is the area starting from a to c, or you can express it as one integration starting from a right here and ends at c. This means that you can combine two integrals if they share one common endpoint. And it also means that you can split your integration, one of them right here, into two parts. But these two parts they have to connect to each other. All right, we did this already when we tried to find the area of the under the graph, and we want to separate between the area that is negative and positive. We did that in class. I don't know if you remember that, but this is what we had to use, right? You can separate the integration into multiple sections as long as they connect to the same continuous range. All right, so these are some properties that let you play around with the definite integral. And last Wednesday, we also talked about the substitution technique. And I want to talk about that a little bit more because we went quite fast. We went through this quite fast on last Wednesday. So let us take a look at this again one more time. If you already understand this, you can also skip this part as well. The point of substitution is that sometimes we have to integrate a certain function that is just too complicated to perform integration directly. This is something, let's take a look here. This is fx. And as you can notice here, this is not something that is in the basic formulas for integration. We have x squared, we have x cubed, we have square root. As you can see, we have lots of things going on, and this is too complicated to do directly in our head, right? Maybe some of you can, but just assume that this is hard. Okay, so in order to make it less hard, we try to simplify it. So we want to use this new variable u to replace some of the terms in these functions in order to make it simpler, easier to solve. All right, but the question is where to put this u in. Which place? Where should I go? Like, should I go with the 3x squared, x cubed, or the whole square root thing? The answer to that is that there is no specific way to substitute u in, because this is about substitution. It's up to you where to put u in. But the thing is, if you put u in the right place, you can solve nicely. But if you put it in the wrong place, you will get stuck. So this comes to the experience. If you do a lot of problems, you are going to start to see where you should go. Right? From my experience, you should be put in the place where it's complicated. For me, I would put u where we have layered functions. What layered functions means is that it's function inside function, or you can say that composite of functions. For me, in this case, I see square root right here. And then inside the square root, I have this polynomial, x cubed plus 1. So here I see polynomial inside a square root, layered function. So I want to simplify this. What about I put u inside this square root to make things simpler? So that comes from my experience. So I'm going to make u equal to x cubed plus 1. All right. X cubed plus 1. Some of you might ask, why not u equal to 3x squared? Or u equal to square root of x cubed? Can we use that? Yes, you can, but it doesn't mean that it's going to come out nicely. You can, and you can try, but if you get stuck, you can switch to something else. So, no specific way to substitute, but just try to find a place that you feel like it's going to solve out nicely. That's the best I can tell you right now. So you can try, but you might get stuck. That's the point. All right. So that is u equal to x cubed plus 1. So let's continue with that. So this is going to be integration, definite integration, starting from x equal to minus 1 and ends at x equal to 1. 3x squared, still there. Square root of x cubed plus 1, but then we have this. We make it simpler. So u is going to go right here. Now, this is going to be with respect to x, just like what we have in the beginning. Now, with this, we cannot just go ahead and integrate. Why? Because we have this variable x right here, variable x right here, and we have u right here. We have multiple variables in one expression. That is not going to work out in the calculation. So we have to get rid one of them. Should we get rid u? No. If we get rid of u, then it's going to come back to the original expression. So the point is, right here we have to get rid of x. Right? We have to continue from the starting point of substitution. All right. So first we try to get rid of this dx. So du by dx, let's do something here. We have this expression u equal to x cubed. Let's diff that. Here we have 3x squared, right? So with this, we know that du divided by 3x squared is going to be equal to dx. With this, we can replace this dx with du divided by 3x squared. Alright, everything else is the same. Minus 1 to 1. 3x squared. Square root of u. du divided by 3x squared. And luckily, it can cancel with what we have at the front right here. I'm not sure if it's lucky. It's more like this case, it's designed to get canceled. It's possible that you might not get this nice cancellation. So it depends. But this case, is designed to get canceled. All right. At this point, I want you to keep in mind that minus 1 right here, this is x. Because we start right here, this is x. So keep this in mind. Minus 1 and 1 right here, this is about x. So let's write everything right here. X equal to minus 1, x equal to 1 square root of u du. Here you can perform the integration right now because we have this square root of u and du right here, so everything is fine. So here you have this integration of u to the power of 1 over 2. That's going to be u to the power of 3 over 2, and then it has to cancel with this power 3 over 2. And you have to evaluate this at x equal to minus 1, x equal to 1. Okay, now from the practice problems that we did on last Wednesday, some of you put 1 straight into u and got wrong answers. And you know why? Because you didn't put this x right here. You just assume that minus 1, you just assume that minus 1 and 1 is for u, but in fact these two values are for x. So in order to use this, you have two methods. So let's take a look here. So method 1, this is what we did in class. We substitute x back into u because we have this, right? So we put this back, so it's going to be x cubed plus 1 to the power of 3 over 2. We substitute back, and this, I'm going to put 2 over 3 right here, and this has to be evaluated at x equal to minus 1 and x equal to 1. Now, no problem, because this is x, and this is x. Okay, 1 goes in, so we have this, well, I can put 2 over 3 right here. 1 goes in, it becomes 2 to the power of 3 over 2. Minus 1 go in, minus 1 goes in, this becomes 0. So in the end, I have this 4 square root of 2 divided by 3. Right? So that's the answer. So in method 1, after integration, we put u back to its original place. That is u. We put x back to its original place of u. So here we sub x back to u. Okay. Now, this is not the only method that you can follow in order to get this answer. You can do another way. So let's take a look here. Method 2. So let's start here. U to the power of 3 over 2. Let's start from right here. And 2 over 3. And you have to evaluate at x equal to minus 1 and x equal to 1. Alright, so we are going to do something different here. Alright, so here, x equal to minus 1, we find out what happens to u value here. So u is going to be equal to x cubed, right here, plus 1. If x equal to minus 1, u is going to become 0. If x equal to 1, then u is going to be 2. Now, x equal to minus 1 is the same as u equal to 0. x equal to 1 is going to be the same as u equal to 2. So in the end, you have this 2 over 3. U 3 over 2 evaluated at u equal to 0 to u equal to 2. Now, you can just put these two values in. So 2 over 3. Now 2 goes in to the power of 3 over 2 minus 0 goes in to the power of 3 over 2. This goes to 0 and it's going to come out to be just the same. Alright, 4 square root 2 over 3. So what is the main difference here? The first one, we substitute x back to u. That's what we did for the method 1. Now, for method 2, what we did differently is that we changed the limit, the boundaries from x values to u values. Change boundaries. Change boundaries to be u values, or you can say u based. U values, right? We make it u equal to 2 instead of x equal to 1, and u equal to 0 instead of x equal to minus 1. So that is the main difference, right? Either way is fine. So which way you prefer, up to you. Now I made a summary about these two methods. In the end, method 1 and method 2 starts the same. You substitute u to the place that you think it's going to work. For me, I like this inside because it's inside another function. And what is difference between the main difference between method 1 and method 2 is the method 1 we just put x back, so we work on the x-based boundary value. Put x back and then we just evaluate the integration. For method 2, instead of put x back, we just stick with u and change everything to u, including the boundary values. Right? You can pick either one. Both of them work. Alright, let's move to the next topic. That is the mean value theorem for the definite integral. Okay, for this video, I might split it into two parts because I think it gets long. So after I talk about this mean value theorem, I might end the video here and I'm going to continue with another part. So mean value theorem. This is for is the main words for this topic. We have seen this before in the proof of the fundamental theorem of calculus, but we have to take a look at this again. So this I need to repeat about this theorem because you have to use it in the later topics of this course. So what this theorem says in terms of concept, it's not much at all. So let's start with this function. We have this function, and this function is fx. Let's assume we have this function, and we are interested in the area under this function. Alright, and this area starts at A and ends at B. We are interested in this area. So if you use the definite integration, this area, blue area, is going to be equal to the integration starting from A to B of this function fx and perform the integration with respect to x. Okay, we are interested in this area. And then this mean value theorem says that if you have this area, it's always possible to find a value c between A and B. Oh, by the way, to use mean value theorem, fx has to be continuous. Keep that in mind. Has to be continuous. So if you have this blue area and this area under this graph fx, it's always possible to find a value c between A and B such that when you find this function value fc right here, you can create this rectangle with the same area as the blue area. That is the whole point of this theorem. If you have a continuous function fx, and if you are interested in the area under that graph from A to B, we are talking about this blue area here, it's always possible to find a specific point between A and B such that you can create this red rectangle which has the same area as the blue. So let's take a look here. Red area somewhere, it's going to be equal to the base of this rectangle, the width, which is b minus a, times the height of this rectangle, which is fc. Right, these two have to be equal. Right, so in the end we have this b minus a fc. I should use red here. b minus a fc equal to definite integration from a to b fx dx. So in the end we have this fc equal to 1 over b minus a square root of integration of fx with respect to x starting from a to b. So this is the formula for the mean value theorem of definite integral. That's all for the main concept of this theorem. Is about blue area and the red area, and they have to be equal. Now the question is, when can we use this theorem? Well, this theorem can be used in different ways. You have seen this in the proof of the fundamental theorem of calculus number 1. We need this to prove that fundamental theorem. But to me, this theorem is, the most common use of this theorem is for finding the average value of continuous function. Alright, so let me erase this slide because I have to use some space here. So I hope you save this, and I'm going to erase this. This is about the use of this theorem. Okay, so the most common use of this theorem is for finding average value of a continuous function over a range. About finding average value of continuous function fx over a and b. A is the starting point and b is the end point. So I need to erase this too. So what does this mean? The average value of a continuous function over a range. So we have this function, and each point has different function value. And I ask you to find average value of this function starting from A to B. Some of you might find this confusing. What does it mean by the average value of a line? So let's take a look here. Let's take a look at an example that involves discrete numbers. What if I give you a set of numbers? Let's say 1, 2, 3, 5, 9. I give you this set of numbers and I ask you to find the average of this set. Can you find that? I think most of you can, because most of you know that average, or the mean, is the sum of all the numbers. That is 1 plus 2 plus 3 plus 5 plus 9 divided by the number of the total numbers here. So we have 5 numbers. So in the end, this is 20 divided by 5. So we know that the average value is 4. Now, what about the average of that? Is it possible to add each values along the line? Just like before, we add each one of this. In the end, we get the average value of the whole set. But here we have infinitely many points along the line. It's impossible to add them all. And in the end, we don't even know how many points we are dealing with. So we need some new definition, clear definition about what average means in terms of continuous function. So what we are interested right here is the average of continuous function. We need a new definition, something that is different from what we are used to. Well, it turns out to be the average height. In this case, in the case of continuous function, it turns out that the average of this is the average height of this line. The average height of this line. So let's take a look here. At the starting point, it has a certain height. Basically, this is function value at fa. So that is the height. And the height increases along the line. Okay? And as you can see, it starts to increase fast and then slower and then fast again. Keep in mind that the average height doesn't have to be in the middle. It can be shifted to the right or to the left. It depends on the geometry of the function. Average point doesn't have to be in the middle. It depends on the shape of the graph. All right. So, in the end, for this definition of the average value of the continuous function, it's the average height. And this average height happens at the point where it creates this red rectangle. So the average height is going to happen right there. Right where we can create this red rectangle that has the same area as the area under the blue graph. All right? Which means that if you want to find the average of the continuous function, it's going to be the same as this FC, because as you can see, the height we are looking at right here is equal to FC, which means that this is equal to the average value of fx over A and B. This range A to B. Right? So basically this is like using the formula for the mean value theorem directly. You want to find the average, just find FC by using this formula. Alright? So here the average of the continuous function, let me put this, it's going to be the average height. And this height is going to be function value that creates rectangle with the same area as area under graph fx. Okay, some of you might got lost during my explanation. So in the end, if you want to find the average value, you just need to use this formula. All right, let's try using it to solve one example, and we are going to end this first part right there. Okay, so let's take a look here. We have this graph function. So this is half the circle, and this function is fx equal to the square root of 4 minus x squared. Alright, and we have this all the way to from minus 2 to 2. We have this line. Let me put a bold line over that. And then you can see that the values start from 0. And it goes to 2 and then comes down to 0. And we just want to know the average value, the average of this line on this range. At this point, we don't know where it's going to be. It could be in the middle, or it could be a little bit higher. So we cannot use the definition we are used to, so let's try the mean value theorem. So mean value theorem says that the average of fx over a and b, range from a to b, is going to be equal to 1 over b minus a integrate of fx with respect to x starting from a to b. Okay, and don't forget that this is the don't forget that this area under graph fx. Okay, so now let's use this to solve for the average of this this half the circle. So we know that a right here is 2 and b right here is sorry, a is minus 2 and b is 2. So b is 2 and a is minus 2. Now we can perform the integration from minus 2 to 2 of the square root of 4 minus x squared with respect to dx. Okay, this here is going to come out to be equal to 1 over 4, and I'm going to keep this just the same, minus x squared dx. It turns out that this terms in this example, it requires another technique. It requires by parts. Integration by parts in order to solve. But we are not there yet. So I'm just going to give you the numbers that it's going to come out to be by using by parts. All right. So after using by parts, this is going to come out to be equal to this red area is going to come out to be equal to 2 pi, which means that in the end you have this pi over 2. Alright, so in this case I want to put the result from by parts just in case if you want to look further into this problem. Alright, so integration of that, integration from -2 to 2 of the square root 4 minus x squared dx. After using by parts, it's going to be equal to x square root of 4 minus x squared divided by 2 plus 4 over 2 arcsin of x over 2. Alright, and you have to evaluate this at 2 and minus 2. At minus 2 and 2. Okay, and it's going to come out to be equal to 2 pi, and divided by 4. In the end, you have this pi over 2. But the thing is, at this point, even though you don't know by parts, integration by parts, you can still answer this. Because at this point, if you understand what the mean value theorem is about, you are going to know that this term right here is going to be equal to the area under graph fx. So it's going to be equal to this area. What is this area? It's going to be half the circle with radius of 2. So area here is going to be pi r squared, and this is half the circle over 2. The r that we have right here is 2, so this is 4 pi divided by 2. So in the end, this is going to be equal to 2 pi. This going to be equal to 2 pi. Just the same as that. You can use by parts to get 2 pi. You can use geometry to get 2 pi. But in the end, you get the average of this fx, and it comes out to be equal to pi over 2. Whoa, sorry. Comes out to be equal to pi over 2 right there. This right there. Pi over 2. Oh, no, not right there. Going to come out to be right here. Function value right here. I'm going to take this out. It's supposed to be a point on the line, right? So either here or there. And as I told you, the average value of a certain function is the average height that creates a rectangle with the same area as the area under the graph. Right. So this is one use of the mean value theorem. As long as you understand about the relation between two areas, you should be able to play around with it for certain on some examples. Right. So we have some more examples to work on. Okay, let me take a look here. Alright, so I have to do this example as well because it's the same topic. It's about mean value. So let's take a look at this. It shouldn't take long, maybe 5 minutes. Alright, so stay awake or please don't give up about this video. So in this case, just like before, we want to find the mean value or the average value of a continuous function. Alright, that's what we want to find. And at this point, we know which formula to use. But then it turns out that this function has two sections, multiple sections. It's equal to x when x is less than 1, less or equal than 1. And it's equal to e to the power of 1 minus x when x is greater than 1. But they want to find the average value of this function on this range from 0 to 3. as you can see here, from 0 to 3, it involves two sections of this function, right? 0 to 1 right here, and 1 to 3 is going to be the second section, which means that we have to consider both of them. However, if the range that we are interested in is just on one section, then you don't have to worry about the other, just take only one. But in this case, both of them. So let's use what we know so far. Average on 0 to 3. Let's use the formula right away. It's going to be 1 over b minus a, right? So b 3, a is 0. Integration of fx dx starting from 0 to 3. Now you should start to notice that we are integrating 0 to 3, and it go over two sections of this, which means that we need to split this integration to associate with the right function for each range. So instead of going straight from 0 to 3, you have to split it. The front part, 1 over 3. Now inside first section from 0 to 1, right? The function is going to be equal to x dx. Now the next section, integration from 1 to 3. Same function, but in this range it's equal to e to the power of 1 minus x. And this is with respect to x. Okay, so let's integrate that. 1 over 3 first term is going to be x squared over 2, and you have to evaluate that at 0 and 1, plus integrate of e to the power of 1 minus x. You are going to get the same thing, but then if you keep it like this, minus 1 is going to show up, but minus 1 is not in the original expression, so I get rid of that minus 1, and I have to evaluate this 2 points, 1 and 3. So here I have 1 over 3. Here I have 1 over 2 minus 0 for the first range. Then the other, I have 3 goes in, this becomes minus e to the power of minus 2 minus, now 1 goes in, it becomes e to the power of 0 with minus in front. So in the end I have this 1 over 3, 1 over 2. This second part, I have this becomes, okay, let me take a look here. This becomes all together, this becomes 1. So I have 1 right here and minus 1 over e squared. So in the end I have this becomes 3 over 2, so this 1 over 2, 1 over 2 minus 1 over 3e squared. Alright, and that is the answer, the average value of this function over this range. Alright, no need to get confused about that. We just need to use the formula from the mean value theorem. But in this case, you need to know that you have to split your integration based on the section that you want to perform that operation.